The book introduces this idea of how to think about probability and movement towards equilibrium, and I think this is a great analogy. Imagine that you have two boxes filled with balls. However, they don't have the same number of balls, so I suppose filled is really not the right way to say it. But you have initially more balls in box 1 than you have in box 2. And what you basically say is that every time you want to do something, right? So what we're iterating over is randomly drawing a number where each of these balls has a number associated with it. I randomly draw a number between 1 and 15, and what's more likely, that I get a number between 1 and 10 or 11 and 15? It's more likely that I get a number that corresponds to this box. So I draw a number and I get 8. What that means is I take ball 8 and I put it over in the other box. So it's no longer here, it's now over here. Good old ball 8. But now I do that again. I'm going to draw a number again. And every time I draw a number, I move that ball. Well, sure, I've moved ball 8, but again, I'm drawing a number randomly between 1 and 15. Maybe next time I get 2. Okay, 2 is no longer in this box, it's over here. Well, now look at what's happened. I now have 1, 2, 3, 4, 5, 6, 7, 8 balls on the left, 1, 2, 3, 4, 5, 6, 7 balls on the right. Initially, I had many more balls in box 1, but now I have almost as many balls in box 2. Now you can imagine that I could start with many more balls that I'm not capable of counting, and this process could continue. But it's random. Once the two boxes have roughly an equal number of balls, it's equally probable that I'm going to randomly pick a ball on the left versus randomly pick a ball on the right. Once the balls are closely matched in terms of their number in the two boxes, you don't expect one box to really end up with more balls than the other, not a lot more. But initially, your initial condition can in fact have a lot more balls in one box than in the other. So over time, they will equalize. And this is reaching equilibrium. So the analogy that we're making here is actually energy, that you can imagine energy being randomly transferred back and forth. But if you start with more energy on one side, you actually expect, simply from probability, that if we're choosing little bits of energy to transfer back and forth and there's more energy on the left, well, you're going to end up transferring energy to the right until they're in equilibrium. So this brings us to probability, and possibly you've studied probability before, in which case this might make a lot of sense very quickly. But there's a lot of different possible states, and probability is just the likelihood that it will happen. So if you have really, really large numbers, n1, and we're talking about, say, 2 states, so again, the balls in our boxes, or we'll talk about coin flips in a second, n1 approximately being equal to n2 is much, much more likely than having n1, for instance, say much greater than n2, or n2 much greater than n1. So let's think about coin flips as an example of this. If I flip 1 quarter, it's 50% probability it lands heads up, 50% probability it lands tails up. If I flip 2 quarters, there's a 25% probability that they're both heads, a 25% probability that they're both tails, and then a 50% probability that one is heads, one is tails. Now let's say we have 1,000 quarters. I can't do the probability off the top of my head, but you would expect, if you had 1,000 quarters and just toss them all up in the air, that about half would end up heads and about half would end up tails, right? That is this condition, that n1 is about equal to n2 because you have about half heads and half tails. If you had almost all heads, you would be really surprised. That's one of these cases. Now, obviously, I could start with 1,000 quarters that I carefully place on the ground, all heads up. I can do that. And then I go through and flip each one. I would expect after I flipped each one that, again, I'm back to this condition. So the point being that I can, in fact, start it in a situation that seems very unprobable, very improbable, that's the word. But then once I've actually iterated it, had some sort of interaction, it's going to keep coming back to that. So equilibrium, where your two states are effectively equivalent, is your most probable state. And again, this is thermodynamics. There's always a distribution. We're not saying that if it must be exactly 500 heads and exactly 500 tails, but say 499, 501, like well, at that point, it's fine, one sig fig. But again, 999 versus 1, that would be really improbable. So equilibrium, where the two states are just about equal, that's the most probable state. And again, we can start it in a state that has low probability. Again, like starting with all of your quarters heads up, but it's really unlikely to return to that state. So if I started my quarters half heads, half tails, I would expect after I flip them all that I roughly have half heads and half tails. Different ones are going to be heads and tails, that's okay. But if I start them all heads up, I expect after I've flipped them all once, it's roughly half heads and half tails. If I keep flipping them, at no point do I expect them all to be heads up. It isn't that it's impossible for them to be all heads up, it's just really, really, really unlikely. So that's the point of irreversibility here, that the individual processes are random and reversible. Flipping one coin, it can be heads, then heads the next time, tails, then back to heads. But once you have a large number of them, if your initial state was unlikely, it's really hard to get back to that simply due to random processes and how probability works. So that is how we can have microscopic reversible processes lead to macroscopic irreversible processes.